Good morning, everyone. I pray that everyone is safe and sound and reunited with their families. It's been a really crazy couple of days, and I'm just grateful that I have my family close to me, and I know that you feel the same. We're going to start off this lesson with just a couple of warm up slides to make sure you remember some things from symmetry and factoring. So take a look at this first one. You want to tell me if it's even, odd, or neither. And so you may need to flip back through your notes to remember how to do that. And pause the video so that you can take the time to practice, and then unpause to check your answer. Okay, hopefully you were able to successfully substitute negative x in place of x in this function. And by the time you finish simplifying, you'll find that f of negative x is equal to the opposite of f of x. And we know that when that happens, we have symmetry with respect to the origin, which makes the function f of x odd. Now try your hand at factoring these polynomials. Remember, factoring is a very important skill as we work with the characteristics of rational functions. Again, pause the video for a few moments, work these out, and then unpause to check your answers. And now you can check your answers to these. Numbers 1 and 2 are your trinomials for factoring. You can factor these by guess and check, or you may have learned the MA chart, whatever works for you. Number 3 is a sum of cubes, and it has its own pattern, so follow that pattern to factor. Number 4, there is a common factor, and the greatest common factor is 4, and once you divide through by that greatest common factor, the resulting expression is a difference of perfect squares, which has its own pattern as well. If you're having trouble with factoring, go to Study Island and complete the factoring lessons to help you out. Now we'll move on to what we really need to do with our lesson. Okay, rational functions. We did an exploration in class, which you should have finished at home, of rational functions, and you found out some things about rational functions. And we know that it's the ratio of two polynomials. So a rational function, we could call it r of x, can be defined by the ratio of two polynomials, p of x over q of x. Very straightforward. First, there's the idea of the vertical asymptote, and these are the lines that we show as dashed lines on the graph. So they're imaginary. They don't really exist as part of the graph itself, but these are lines where the graph approaches but never touches, never crosses. And these occur at values where the rational function is undefined. Remember, a rational function is undefined anytime the denominator equals 0. The horizontal asymptote is an imaginary horizontal line. Think about end behavior on the graph. So this line represents where the rational function will approach or get really close to on its ends. And it has the equation of y equals some number because it's a horizontal line. And then there's the domain and range, where the domain is all possible inputs for a function and the range is all possible outputs for a function. So let's take a look at how we find some of these, or really all of these. Now there are 3 cases for finding horizontal asymptotes. We have to pay attention to the degree of the numerator and the degree of the denominator. And I will denote these as d sub n for degree of numerator and d sub d for degree of the denominator. So when the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is the line y equals 0, which is nothing more than the x-axis. So a graph like this will approach the x-axis as its end behavior. When the degree of the denominator is equal to the degree of the numerator, then the horizontal asymptote is actually a fraction where y equals one number over another, where those numbers represent the leading coefficients of that particular polynomial, of those particular polynomials. And we'll see an example of that shortly. When the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. However, there may be, not always, but there may be a slant asymptote. And again, I'll show you an example of that one. So beginning with this first function, 3 divided by that x minus 1, let's look at the vertical asymptote first. If this denominator is ever 0, then we cannot proceed, as this would not be a defined function. So we are looking for values of x that make the denominator equal 0. It's a very quick set x minus 1 equal to 0. You can even throw the not equal in there to help you understand what cannot happen. So in this case, x cannot equal 1. So the equation of the line for our vertical asymptote is x equal 1. As far as the horizontal asymptote, the degree of the numerator is 0, considering there is no x value that's like x raised to the 0 power. The degree of the denominator, the highest power of x, is the exponent 1, so the degree of the denominator is 1. Considering that the degree of the denominator is, the degree of the numerator is less than the degree of the denominator, that means that our horizontal asymptote is the line y equals 0. So now as we look at the domain is all of the possible values we can input for x. And we've just seen that we can input any value except for 1. So writing that in interval notation, we begin with parentheses at negative infinity, x values, and we can go all the way up to whatever that last value is right before we get to 1. So 0.999999 on forever, just not 1. So we close off 1 with parentheses. And then we combine that through a union symbol with values that are just on the other side of 1. So 1.00000 forever, ever, ever, and then maybe a 1 at the end, all the way up to infinity. So this is our domain. Now as far as our range, remember that it is possible for the function to cross at its horizontal asymptote. To see whether or not that happens, what we need to do is to take our function, set it equal to that value of y, and see what possible x values we can get out. So let's take a look. We have 3 over x minus 1, and we want to set that equal to 0. Again, that's coming from the value of the horizontal asymptote. And we solve for x. Well, when we begin to do that, multiplying both sides by x minus 1, we get a statement that says 3 equals 0. Well, of course, that's not true, which lets us know that our graph does not cross its horizontal asymptote. So the range y values, we start at the bottom, negative infinity, and we come all the way up to whatever that last negative number is right before we get to 0, close it off because 0 is not included, and then combine it with that first positive number after 0, and then we go on to positive infinity in the y direction. So these are the characteristics of our graph. So now let's look at how that graph would actually appear on a coordinate plane. And so here's the graph of that function, 3 divided by the quantity x minus 1. And you can see your horizontal asymptote here. And you can see the end behavior in that the graph is getting closer and closer and closer to 0. On the which is the x-axis, and we can also see our vertical asymptote here as the graph is getting closer and closer and closer to 1, but we know that it will never touch 1 on the x on that vertical line. It will never touch 0 across that horizontal line based on what we just talked about with the other characteristics. Okay, here's one that's slightly different. The vertical asymptote won't change considering this is the same denominator, so this is still the line x equals 1. And because of that, the domain won't change either, negative infinity to 1, union 1 to infinity. Pay careful attention to your notation on your domain and range. Now for the horizontal asymptote, we now have the degree of the numerator as 1. That's because the power that we don't see on the exponent for x is the number 1, and there are no other variables in that polynomial. The same will be true for the denominator. The degree of the denominator is also 1. And so we see that the degree of the numerator is equal to the degree of the denominator. When that happens, your instructions say that the equation is y equals the ratio of the leading coefficients. Well, what we mean is look at the numbers that are in front of that highest power of x and we're going to divide those to figure out the value of our horizontal asymptote. So in this case, y equals 3 over 1, or 3. So that's our horizontal asymptote. Now, we need to figure out whether or not the graph actually crosses its horizontal asymptote so we can have an idea of what our range is for this function. So again, we take our equation and we set it equal to that value. So we take 3x over x minus 1 and we set it equal to 3, and then we solve and determine values of x where this equation may be true. If we multiply both sides by x minus 1, we get 3x equals 3x minus 3. And then as we begin to solve for x, we'll get something that says 0 equals negative 3, which is not true. Again, what that tells us is that this graph does not cross our horizontal asymptote. And so our range will begin at negative infinity, and it will go up to 3. And we pick up on the other side of 3 all the way to positive infinity. These are the characteristics for that graph. So this is the graph of 3x divided by x minus 1. Again, you see your vertical asymptote here, your horizontal asymptote here. You can plug in 0 for x and find where the graph crosses the y-axis, and you can plug in other values through a t-table for this. We can look at that more specifically in class. Alright, one more here. So now we're looking at 3x squared over x minus 1. And again, vertical asymptote does not change. Horizontal asymptote, the degree of the numerator is now 2. The degree of the denominator is still 1, but this time the degree of the numerator is greater than the degree of the denominator, which means I don't have a horizontal asymptote. But I may have what's called a slant asymptote. So we'll need to look at how we find that. If the degree of the numerator is exactly 1 higher than the degree of the denominator, then we have a slant asymptote. And the way we find it is through polynomial division. Now this one we can use synthetic division since the divisor is a linear factor. So with x minus 1 being the divisor, the root would be 1. And so we set that up as 1. And we divide that with 3 as the x squared, 0 is the x, and 0 is the constant term. We bring down our 3. 1 times 3 is 3. And remember, and then we add these to bring it down. So this is a 3. And then 1 times 3 is 3 here. And we add again to bring these down. That last one is our numerator. So the descending polynomial would be 3x plus 3. So we'd be rewriting this as y equals 3x plus 3 over the divisor, which was x minus 1. But we only need this quotient part for our slant asymptote. So that's our slant asymptote. If we had to do this the long way, we would take x minus 1, divide it into 3x squared. We put in placeholders for 0x, and 0 is the constant term. We take a look at x and ask ourselves, what do we need to multiply in order to get 3x squared? The answer to that would be 3x. And then we multiply 3x times x for 3x squared, 3x times negative 1 for negative 3x, and then we would be subtracting these. And so this would give us a positive 3x here. And then we ask ourselves that same question about x and 3x. What do I multiply by x to get 3x? The answer there would be a positive 3. And then I multiply back by 3. So 3 times x is 3x. 3 times negative 1 is negative 3. And remember, I would be subtracting those. And so then that becomes a 3. And there's nothing I can multiply by x as a whole part number or polynomial to get 3. So I'm left with that same 3x plus 3 there. So now I have a slant asymptote at y equals 3x plus 3, which is a line. That's a linear equation with a slope of 3 and a y-intercept of 3 as well. Now it may be helpful to know whether or not the graph crosses the slant asymptote. So we set the function 3x squared over x minus 1 equal to the expression for the slant asymptote to see if we can find x values where this actually occurs. And multiplying both sides by x minus 1, we have 3x squared equals 3x squared minus 3x plus 3x minus 1. And by the time we start to solve for x, we'll have something that says 0 equals negative 1, which is not true. That lets us know that this graph does not cross the slant asymptote. Now, to find the range with a slant asymptote is challenging unless you have a graphing calculator. So on the next slide, I show you what we can use the graphing calculator for to help find the range. So what I've done is graph this, and I've used the trace features and the calculate features to find the local maximum and the local minimum around the slant asymptote. So remember, we did not have a horizontal asymptote. The vertical asymptote is 1. My graph is scaled by 2s, so we're looking at the line x equal 1 come like right in the middle of the 0 and the 2 mark. And then we have this line y equals 3x minus 3 for our slant asymptote, plus 3 for our slant asymptote. So the slant asymptote would be a line here that has an intercept at 3 and kind of goes this way for that graph. So the graph is bounded by x equals 1 and y equals 3x plus 3. So the range, it appears, begins at negative infinity on the y and comes all the way up to 0 on the y-axis. And then it doesn't pick up again until 12 in the y direction and carries on to positive infinity. So our range is negative infinity to 0 union 12 to infinity. And these should really be brackets because 0 and 12 are actually part of the graph, but parentheses on the infinities. So that one is a little strange because we can't find the range directly as we did before because of the slant asymptote. Okay, almost done. This is the last part. Sometimes there are holes in the graph, also known as points of discontinuity. And these are not entire lines where the function is undefined, but just certain little blips in the curve, so to speak, where they're undefined. So what we have to do is to factor the numerator and the denominator, and if there are any common factors top to bottom, then we know that we have holes in the graph at the x value of that particular factor. So we'll start with this example, and we're going to factor it. Now, in order to make this a little easier for some, I'm going to turn this numerator around and make this x squared plus 3x minus 28 over x squared plus 12x plus 35. And so if we factor those, we have x plus 7 times x minus 4 in the numerator. And we have x plus 7 times x plus 5 in the denominator. So we can see that there's a common factor of x plus 7 in both the numerator and the denominator. So that lets us know that we have a hole, is what we call it, or a point of discontinuity, definitely at x equals negative 7. Just solve that, set it equal to 0 and solve for x. Now, we need to know the value of y at that point. So to find the value of y, what we do is we take this negative 7 and we substitute it in for x into the non-common factors. So the y value would then be negative 7 minus 4 over negative 7 plus 5, which is 11 halves. So we actually have a hole at the point negative 7, 11 halves, which is 5.5. So that's going to come in handy. Now, we also need to find vertical asymptotes, horizontal asymptotes. So look at the denominator for the vertical asymptotes. Usually we would set all factors equal to 0, but being that we know there's a hole at x equals negative 7 and not a vertical asymptote, we're really just going to focus on the non-common denominator. So we're going to have a vertical asymptote at x equals negative 5. For the horizontal asymptote, we're going to go back to the original function and we're going to compare the degree of numerator and denominator. Degree of numerator and denominator are equal, so we need to be focused on these ratio of coefficients for that leading term. So 1 divided by 1 is 1. The horizontal asymptote occurs at y equals 1. Because there's a horizontal asymptote, there will not be a slant asymptote. So our domain, we have a hole at -7, and we have a vertical asymptote at -5. So we're going to go from -infinity up to -7. And we're going to combine that with -7 up to -5. And then we're going to combine that with -5 all the way to infinity, because we have no more points of discontinuity within that last range. Now, for the range itself, it can be a little interesting. For range, we want to know if our function crosses its horizontal asymptote. So we set the equation itself equal to that value. So this would be 3x minus 28 plus x squared divided by x squared plus 12x, a little sloppy there, sorry, x squared plus 12x plus 35. We want to know if it's possible that that can equal 1. Multiply both sides by the denominator. I'm going to reorganize the terms on the left side. So we have x squared plus 3x minus 28 equals x squared plus 12x plus 35. And as we begin to solve for x, we'll have 3x minus 28 equals 12x plus 35. Continue to solve. I have 9x negative 63, which will lead me to x being -7, but I know I have a hole at -7, so I can't possibly cross the horizontal asymptote at -7. So my range then, remember I have a hole at -7, -5, or positive 5.5. So my range goes from -infinity up to that 5.5, and then I union that with 5.5 to infinity. That was really messy. Let me rewrite that. Sorry about that. So we're going to go -infinity to 5.5 and union 5.5 to infinity. So that concludes rational functions. Oh wait, sorry. I wanted to show you the graph. Hold on. We'll go to the graph of that. Okay, here's the graph of that function. We can see our horizontal asymptote at y equals 1. Our vertical asymptote at x equals -5, so getting really, really close to that, but never touching it. And then even though you can't see it on the graph, we'd have to zoom in really, really far in order to be able to see it. At -7, about 5.5 here, technically there's a hole in the graph. The graph is not defined at that point. And we literally represent that by putting a little hole at that part of the graph. So hopefully this is giving you some insight. Watch this video or parts of it as many times as you need to. There's also a worksheet in the Unit 2 folder that you will need to complete. And if we're not in school tomorrow, there'll be another worksheet for you to practice. Post any questions that you have on Edmodo. If there are any mistakes on there, please forgive me, bring them to my attention, and we can correct them through discussion. I hope you guys have a great day. Thank you.